So welcome to the third lecture on competition policy. So today we're going to look at the Bertrand markets, so markets in which there is price competition, and in particular to estimate the effects of mergers. We will here introduce the concept of merger simulation, which is basically a methodology that has been used in several cases, and we'll have a look at some such cases. So last week, of course, we looked at horizontal mergers. And in particular, we looked at Kuno markets, so quantity setting markets. So we had a look at the merger paradox, in which we found that typically for firms to benefit from a merger in a Kuno market, we actually need a merger to almost monopoly. So that's sort of weird in the sense that we see many such mergers, even in markets which we might characterize as typical quantity setting markets, where capacity constraints perhaps play a big role. So the question then rises: why do we see this? Why do we see these mergers after all? And last week actually we had a look at the answers partially provided by the Farrell and Shapiro paper, which relies mostly on cost efficiencies to explain why mergers might be attractive even in those markets. So this week we'll have a look at price competition. So the reason why in Kuno markets, so in quantity competition, these mergers might sort of not be so favorable for the emerging companies, although they might be very favorable for the outside rivals, is that if you merge and as a result you will shrink your output in the Kuno market because you want to raise prices. But in response in Kuno markets, we know that rivals will then expand their output. So they will partially undo basically the market power effects that are created by the merged entity. Now this is actually completely different in a Bertrand market, because in a Bertrand market, if one player raises its price, well, the reaction functions in the Bertrand market are actually upward sloping. So that will mean that rivals will raise their price as well. So this is going to accelerate basically the efficiencies in terms of gaining market power of merging with other companies. So these are different. So it's going to be easier typically in Bertrand type and pricing markets, price type markets, to benefit from your own increased market power. So both the insiders and the outsiders will benefit. So let's have a look at that. So let's have a look at price competition first. So that will be first part of this of today's lecture, and after that we'll see how we can actually apply the general Bertrand model to realistic models of actual mergers. This will be the topic of merger simulations, and we'll have a look at the various examples of these of merger simulations and how we can estimate those essentially. So what again is different with Bertrand competition? So typically we want to have a look at Bertrand competition with differentiated goods, right? Because otherwise, even with two companies we would already have, if they would be exactly equal, we know that prices will go down to marginal cost, and there will be no market power even with two companies. Well, in reality, Bertrand competition will happen among firms which produce differentiated goods, and in that case this differentiation essentially creates some market power. So you can think about consumer good markets, stuff that you buy in supermarkets. It's typically price setting that is the mode of competition in those markets. So we need a model, essentially the Bertrand model, to reflect that we have different goods which are priced but which might be slightly differentiated. The typical way in which we model differentiated goods is by looking at in this partial equilibrium framework of competition. We would like to look at utility for consumers, which will be linear and money here. So that's what we assume, but which might have if there's n different goods, and you might, as a typical representative consumer, by quantities of each of these kinds of goods. So these quantities here are denoted by Q1 up till Qn for the n different goods. And you will get some satisfaction, essentially some utility from consuming these quantities of goods. But of course, you have this utility of having to pay for them, and so the advantage or the utility from consuming those goods is the first part here, and the second part is what you're paying. So you're paying, if you buy a quantity Q1 of good 1, you will be paying P1, the price for this good, times Q1, etc. up to Pn of the Qn units of good n that you're buying. So this being your utility function, what would you like to do as a consumer? Well, you would like to select the quantities of these goods to consume that are going to optimize your utility. So what you would do essentially is to maximize this utility that you get. So maximize over the quantities that you're consuming. So by doing, how would you do this? Well, you would basically, mathematically, you would try to find the maximum by taking the first order conditions essentially. So taking the first order condition over the quantities means, I take the derivative, for instance, for good 1, I would take the derivative of my u, my utility, with respect to quantity 1. I take the derivative of all these terms, well, actually only this term over here actually has a Q1 in there. So if you take those derivatives and set them equal to 0, what you find that indeed prices are going to equal the derivatives in equilibrium, are going to equal the derivatives of this u. So essentially the derivatives of the utility with respect to quantities will equal price. So this essentially will become the essentially the inverse demand for this for the goods in this market. So let's have a look at how this might work in practice. So we might have a two differentiated good market which have utilities here, u, which is a function of how much you consume of each of these goods. So what would be the demand functions, or rather the inverse demand functions that would have in this market? Well, we have to basically do use this concept that I just, or this result that I just introduced here, that price will equal the derivatives of partial derivatives of utility. So let's do that, and of course I'm going to do this on paper. So let me switch to paper here. So we have the representative consumer, who from consuming quantities Q1 and Q2 will get some utility Q1 plus Q2 minus Q1 squared plus Q2 squared plus Q1 Q2. So what's the demand equations that go with this utility function? So what we need to do is we need to write down the price for product 1 in equilibrium will be the partial derivative of this utility with respect to quantity 1. So that's basically the demand equation that you know from your micro courses. So let's work that out. We have a Q1 over here, so that gives us a 1. If we take the partial derivative, of course, Q2, taking the derivative of Q2 with respect to Q1 gives nothing, gives 0. But here we have some additional terms. So in particular, this Q1 squared gives me minus 2 times Q1. Q2 squared again vanishes if I take the Q1 derivative, but here we have an additional minus Q2. So this is the demand equation for product 1, and similarly we of course have a similar demand equation for product 2, and that will be of course minus 2 times Q2 minus Q1. So this these two goods in this case are actually symmetric, but they're differentiated, so it's not the case that you will only buy good 1 and not good 2, and in general that you might buy a mixture of those because they're only partial substitutes. So let's have a look. These are the inverse demand equations. What would be nice actually is to also have the demand equation. So these are prices in terms, how do prices depend on demands? So P1 is a function of Q1 and Q2. P2 is a function of Q1 and Q2, but we might want to know as well what is Q1 as a function of P1 and P2. So in order to find, and similarly for Q2 of course. So in order to find that, we need to invert this demand system, right? So what we have to do is, well, we know P1, let me just rewrite this, what we had already. First equation, second equation. We now have to sort of isolate here the Q1 and the Q2. Minus 2Q2 minus Q1. So what I'm going to do is, and so I want to say I would like to get rid of the Q2 parts over here, so I can basically get an equation for what Q1 is going to be in terms of P1 and P2. So this is just a set of two linear equations in two unknowns, essentially Q1 and Q2. I want to know what both Q1 and Q2 will be in terms of the P's, the prices. So let me eliminate essentially the Q2, for instance. So let me to do so multiply the first equation by 2 to minus 4Q1 minus 2Q2, and here let's keep this P2 equals 1 minus 2Q2 minus Q1. So why did I do this? Well, of course, now we have the 2Q2 in both of these equations, so we can actually take the difference between these two equations. What does this give us? On the left hand side we have 2P1 minus P2 equals 1 minus 4Q1 minus Q1, so that makes minus 3Q1. And of course, you know, the whole thing, why we did this basically is that the Q2s here are vanishing. So minus 2Q2 minus 2Q2 equals 0. So this is the equation that we will use for isolating Q1. So what's that going to be? 3Q1 is going to be 1 minus 2P1 plus P2, or in other words, Q1 is going to be 1/3 minus 2/3 P1 plus 1/3 P2. So we've inverted the inverse demand system essentially. We figure out what Q1 is in terms of P1 and P2, and doing much the same computations, similar. We'll find that Q2 is going to be, it's completely symmetric, so that's going to be easy to write down without actually doing the computation. Will be of this form. So this is the demand system, right? So this is the regular demand form. So Q1 as a function of P1 and P2, and Q2 is also a function of P1 and P2. So what we see is what happens if you raise P1, if the company's, in particular firm number 1 is going to raise its price, P1, of course. So if P1 is going to go up, what we see is that Q1 is going to go down, Q1 is going to go down, but also something is happening to the quantity of good 2, the rival's good if you wish, and that's going to increase. Q2 is going to go up. So what this means is basically these two goods are substitutes. If the price of good number 1 is going to go up, people are going to shift their demand away from good number 1 but towards good number 2. So let's go back then to the slide to see that in action again. So here's the same same computation essentially. So here we did this is what we did, basically deriving what the inverse demand is. Then we inverted that. I just did that on paper, so it gives us the actual demand equations, quantities as functions of prices. And we see indeed these, well, first of all, the own price effect. So Q1 is going to decrease as price for product 1 is increased. It's reflected by this minus sign. But on the other hand, Q1 is going to increase as the price for good 2 is going to increase. So that means some demand from good 2 will then be shifted towards good 1. So these two goods again are substitutes, partial substitutes. The differentiated partially substitutes. So what's then Bertrand competition? So we now know what the quantity is a function of prices is. So if each firm now only sells one product, then well, each firm will have a profit by I, by 1 or by 2, which is what the margin they would make on each unit of profit, the price margin, price minus marginal cost that they make on each unit that they sell, times the number of units that they sell, which will depend on both price 1 and price 2. So this boldface P, just the shorthand for P1 and P2, if you wish. And the second, the first order condition here is this. So what are you going to do if you're the firm? If you just sell one product, you're going to take you're going to make sure that you're maximizing your profits by optimizing price. So you're going to satisfy your own first order condition. So that means I'm going to take the derivative with respect to price, because you're setting price, gives us a Q by taking the derivative over here, but also gives us this second term by taking the derivative of Q with respect to Pi, and that's this. And you can rewrite this a bit and divide this by P to get a sort of manageable equation here, where on the left hand side you recognize P minus C over P, which is the relative markup, the learner index, as I have called this before, I think. And that turns out to be equal, to be easily expressible as minus Qi divided by Pi divided by this derivative, this own price effect essentially. And well, this is nothing else but the own price elasticity epsilon II of this good, which will be negative number actually. So the learner index is 1 over the own price elasticity with a minus sign, since this own price elasticity will typically be a negative number. Okay, so that happens if there's just two different firms that are competing in this market of these two differentiated goods. What happens if one firm has a lot of products, or 2 products, or more products? Well, in this case, you are going to, when setting your prices, you are going to take into account, well, if I raise my price for product I, of course, I'm going to lose some sales in product I, but of course, I also make some additional margin on any sales that I do make. That's what we had before already, so those things are balanced. But now there's a separate, an additional effect as well. So it's going to happen as well is some consumers who are not going to buy this product I because it gets too expensive, will shift to other products. But those other products, some of those I own as well. So my sales in the other products in my own portfolio are going to increase if I increase the price of one of these products. And that actually is going to give me an increased incentive to actually increase prices. I will gain by price increase also by benefiting from this increase in sales of my other products that I also own. So how would we do this computationally? Well, we would have the whole firm's profits in this case will not just be the profits over firm I, but would be the sum of the profits over all the products I that are produced by this particular firm F. So that perhaps if this firm produces goods 1, 2, and 3, then the I equal 1, I equal 2, and I equal 3 would be part of this firm. So my total profits would be the sum of all those profits on each of those individual products. And I also have to take into account the effects of the increase in quantities of those other products if I increase my prices of product I. So how do we see that happening in the first order condition? Of course, take the derivative of pi f with respect to pi, gives us on the firstly the pi over here, which just is multiplying qi, so this gives us this first term qi. But secondly, we will have the impacts on the sales of all the goods in my portfolio. So not just good I, but also the other goods that I have in my portfolio. And those, this dq dp will be positive because I will have this positive cross price effect. And they will multiply by the margin that I'm making on those products. So I have to add all these up. So this addition of all these extra terms here will make sure that the resulting optimal price for me is going to be higher. So what does that mean in terms of merger? Well, if I merge with another company, I will also get those products into my portfolio, into my own portfolio. So I'll add essentially in the first order condition these additional terms of those products in my portfolio, and that will give me a drive to actually raise my prices of all my goods, which now have internalized the shifts of sales from good, say 1 to good 2. So when is this effect larger? When you merge, in particular with close competitors. So when this D.Q.J, DPI is a large positive number, so with large cross elasticities basically. Large cross elasticities means these goods are close substitutes, so there's going to be a lot of shift of quantity from good 1 to good 2 if you raise prices of good 1. So that's the baseline here. That's the Bertrand competition with differentiated goods. So we know that merging means having a larger stimulus, larger incentive to raise prices. So when you raise prices on all your products, and you will benefit actually, and also all your rivals will follow suit to some extent because they will have upward sloping response functions. So the next step that we're going to make is to look at how this would work in an actual merger. So if you want to look at an actual merger, can't we just use this model of Bertrand pricing in differentiated goods market to predict essentially what the resulting rise of prices will be? So we'll have a look at that in a bit.